Hello, my name is Mr. Adams, and this is a video on buffer theory. Okay, before I move into the topic, right? Please check out my site, Basic Chemistry for Pre-Nursing and Regents. Okay, it's on YouTube, and it's all free. And all I'm asking is please like and subscribe. Okay. Also, guys, if you know anyone in nursing school, or trying to get into nursing school, having issues with the boards or any other subjects, have them check out this site right here, adamsnursingreviews.com. It's a one-stop shop for all their nursing needs. Okay, so we're moving into this topic of buffers, right? Now, a buffer is a solution where if acid or base is added, okay, the pH of the buffer solution will not change significantly. Remember in that we have buffers in our blood, and specifically we have the H2CO3, right? HCO3 minus combination working together. Now, before I get into that, please review these topics: conjugate acid-base pairs, equilibrium constant expressions or K expressions, Le Chatelier's principle from equilibrium, and know your strong and weak acids. Okay, these three guys, the first three guys, I have videos on them on my site, so you can check them out. And you could look up the strong acids, and all the other acids will be weak. Now, in terms of conjugate acid-base pairs, a simple thing is that the only difference between them is a proton. And a proton in this topic of acid-base chemistry, okay, and conjugate acid-base pairs is H plus. So they have the H plus difference between them. So that's how you know. Now, in terms of blood having this buffer in it, right? If blood did not have the buffer, we know that the pH would spike up or down depending on whether a base or acid was added, and a condition called alkalosis, okay, or acidosis, okay, can occur. All right. Now, alkalosis is when the pH is too high, and alkalosis is when the pH is acidosis is when the pH is too low. Okay, so we got to watch out for that. Okay, so also here's another example. Let's say we have pure water here, right, in this my fancy Erlenmeyer flask, right, and we add 0.1 big M or 10 to negative 1 big M molarity of base to it, right? What's going to happen is the pH of the pure water solution will spike up significantly, okay? It will go up probably to around pH 13 or so. Now, we know pure water is 7, right? Now, also on the flip side of that, if we, right, add 0.1 or 10 to negative 1 molar concentration of acid, the opposite will happen. It will shoot down to a value of around 1, okay, or close to that. Now, once again, if that happens in a living system, like for us in our blood, that will be fatal. Okay, so we use something called a buffer. Now, a buffer is made up of a weak acid, right, and its conjugate base. Okay, we just said before that weak acid and its conjugate base, how do they differ? By a proton difference, right? So I underlined it here. This is our weak acid, and our conjugate A minus base right here is over there. Now, HA is a universal representation, right, of any, okay, weak acid for us, and A minus would be the universal representation of the conjugate base when we took away the H plus. Now, what happens, everyone? What happens when we add more acid to this system that's at equilibrium? So we have HA plus water, H2O, and it's in equilibrium with A minus and H3O plus. Okay, so we know it's moving back and forth at equal rates. When we add more acid or add more H3O plus, or H plus if you want to, that's a stress, right? So what's going to happen is this A minus will react more with the extra H3O plus and shift the equilibrium to the left, okay? Alrighty, so what's going to happen is you will have more HA being produced. So more HA is going to be produced. I should draw that from the original amount. And we're going to lose some A minus, all right? Okay, so the A minus amount will go down a bit. So then do that from our original amount. So it goes down. Alrighty. So what overall, though, the ratio that we originally had does not change that much, okay, from what we originally had. Okay, let's try again. What happens if we add more base? Now, let's say we represent base, right, as OH minus, right? Concentration of OH minus. What's that going to do? That's going to remove our H3O plus. Remember, this original reaction was an equilibrium moving back and forth at equal rates. When we remove that H3O plus, that's a stress, right? So what's going to happen? The reaction will shift this time to the right. Okay, why is it doing that? Because we're taking away H3O plus over here by reacting it with OH minus. This HA, right, will ionize and produce more of the products. It will produce more A minus and more H3O plus, trying to relieve that stress. So if this is HA, right, and this over here is our A minus, right? What's happening? We are losing, okay, some of our HA, so the amount goes down. But on the opposite side of that, we are going to gain some more A minus. So from the original ratio amount, it does not change that much. So once again, the conjugate acid and its base, okay, the weak acid and its conjugate base, they're working together, right, to relieve the stress of any addition of extra acid, H3O plus, or any extra base, OH minus. Okay, so let's wind down. We have this reaction right here, and I wrote here the K expression. Please review the K expression. I have a video on that, the equilibrium constant expression. This is the K expression for acids to show how it ionizes and the ratio of the products over the reactants. All right. Notice that water is not inside of the K expression. Okay. So here we go. If you take the log, right, of both these sides right here, and you do some simple rearranging, you will get something called the Henderson Hasselbach equation. And that equation simply states that pH is equal to pKa plus log of the concentration of A minus over the concentration of the weak acid. Okay? And this equation is very, very important in solving buffer problems, simple buffer problems or more complex ones. This ratio right here, okay, once, okay, it's not affected that much, your pH value will not be affected that much. Okay, so once again, the buffer in terms of the weak acid and conjugate base is very critical in terms of how this ratio is affected. Once it's not affected much, it doesn't change much, your pH won't change much, and your system will be happy. Okay, guys, on my next video, right, I have, it's going to be on actual buffer calculations, where we'll put this Henderson Hasselbach equation to use. Okay, so winding down, please like and subscribe my site. Okay, it's called Basic Chemistry for Pre-Nursing and Regents. And please check out adamsnursingreviews.com. Okay, all right, take care.